Hello, everybody, and welcome to episode 4 of our 5-part workshop series on cloud management. Today, we're going to be getting a lot deeper into the engineering side of things and applying the principles that we've presented through episodes 1 through 3. So let's go ahead and get into it. So first off, a little bit about myself. Hello, everybody, and welcome to episode 4 of our 5-part workshop. My name is Colin Newberry. I'm the Director of DevSecOps at Yahara Software. My role is to lead our DevOps and cybersecurity practices. I have nearly 2 decades of experience in this field, and I'm happy to share as much of my experience as I can. All right, so our schedule for the series, we are now on episode 4. We started with our foundations on October 21st, moved on to our modern mindsets, project management, and next week we'll be talking about waste management. So to start things out with a recap, without strong foundations, everything else will collapse. So before you start any kind of transformation into new practices or processes, new tool adoption, really any kind of digital transformation, you need to start by building a foundation. That starts with understanding your organization. Who are you? Where do you sit in your organization? Who are your key stakeholders, your customers? Who's responsible for your teams and their career growth? Make sure you actually know responsibilities of members of the team. This shouldn't just be a chart with some lines and some pictures and titles on it. This needs to actually clearly document who's who within the organization. You need a decision framework. One of the most expensive things that happens in DevOps and really any engineering practice is decision paralysis. Remove ambiguity from your decision-making processes. Make sure timelines and expectations are well known, and remove fear from the process of making decisions. People should be confident that they're making decisions that they are appropriate to be making. Have a comprehensive style guide. Make sure everybody is on the same page. This is really important in DevOps, where we traditionally don't actually manage the style guides. But with how much code we actually write these days in our infrastructure practices, having a clear and comprehensive style guide prevents drift, keeps everybody on the same page, ensures maintainability of our code, and generally reduces our cost and complexity of maintaining our environments. Having a clear onboarding process will keep engineers active and working. It will get people through the door and to a state of productivity much faster. The old way of putting an engineer on a project and saying, call me if you have questions, doesn't actually work. You end up with a lot of issues between your different environments and a lot of drift between your playbooks and projects. Once you have a foundation, you can start building your structure. So the mindset we want to follow is that of microservice architectures inside of our infrastructure. This works really well for us in infrastructure as code because data centers are actually not intended to be monolithic structures. Every component of a data center, from routers, switches, servers, hypervisors, they are all discrete, segmented components that have single functions. And that is exactly how microservices are intended to work. This also gives us the power of reuse. When microservices are used instead of monoliths, we can completely reuse 100% of the code we write, which is what we're actually going to take a look at today. And that'll reduce our maintenance budgets, the time required to build new projects, and will improve the general complexity of understanding how projects are deployed in the end environments. So we had a problem here. What was that problem? The problem is that we are not doing this from greenfield. Most organizations are starting with years, if not decades, of technical debt from production data centers that have been running and need to keep running. We can't tolerate long outages, so we need to manage to zero downtime expectations. There are other options for our customers, and we can't allow our transformation and our new practices to cause customers to want to look for other options. We have to understand that this takes time. It's not something that's going to happen overnight. And we need to manage expectations within our stakeholders. Visibility is key in keeping the executives and our stakeholders bought into our processes. So what we're going to talk about today is actually getting our hands in some code, and we're going to get out of the slide deck here in just a little bit and bring up Visual Studio. And we're going to talk about a disaster recovery scenario. To preface that, there are three types of disaster recovery sites. There's the hot site, which is very expensive, always available. We are literally running a copy of our production data center in another location. This is the most expensive but most reliable way to do it. We have warm sites, which are not as expensive, but they're also not always available. We keep key infrastructure that takes a long time or is complex to deploy available, and all of the other components that make it work are kept offline. Still relatively costly, but definitely not as costly as a hot site. Usually takes days. Sometimes you can get it down to hours to recover from a warm site if you have a small enough environment. And then, of course, there's the cold site. All we're keeping is a backup, an offline backup somewhere that is not tied directly to any databases. There is no infrastructure behind that to stand it up. And when something happens, we kind of just pray it works. There is a lot of risk in running a cold site DR strategy. So why does a cold site not actually work? Number one, we have knowledge gaps. From one engineer to another, if an engineer leaves a project, they take knowledge with them. If we don't have a foundation where we've clearly documented how things are done at our organization, if we don't have a style guide which clearly shows how code is written and how modules are composed into templates and environments, then we're going to have gaps in our knowledge that are going to prevent us from being able to deploy a disaster recovery scenario from a cold site. This leads to the problem of it's easier to do it in the console, especially in cloud. It is very easy to make changes in the console if you have the right permissions. So when we do our codified playbooks for the day one deployments, if we were lucky enough to do it from Greenfield in code, day two, a developer may have run into a critical problem and had to go and make a manual deployment. That became technical debt. That technical debt eventually may or may not get solved. In the meantime, it leads to drift. And as we continue to drift over years and then decades, our disaster recovery becomes unmanageable. Luckily, there's a solution. We can solve knowledge gaps with foundational documentation. If we document how we do things, if we have these clear, structured documents that tell every team member how to do their work and how we expect our level of quality to be applied, we won't have the same knowledge gaps. An engineer leaving isn't a key risk. We can template out our environments with version-controlled modules, and I'll show an example of a version-controlled module in a little bit here. And this will help us prevent technical debt from building up, because projects will not actually be writing code for their infrastructure. They'll be consuming already written code. And then, of course, managing the existing drift, because, like I said, most of us are not doing this today from Greenfield. We are working with existing technical debt, some of us with decades of it, and so we need a properly managed project to be able to handle that. All right, so getting into the actual code. So this is going to be done in Terraform. Terraform is by no means the only place you can do these practices. This can be done at any declarative infrastructure tool. I use Terraform because it's what we use extensively at Yahara Software. It is probably the most popular infrastructure as code tool on the market today, and so it's a great place to demonstrate this. Just to show something real quick here, I do have our dev site up and running. So we're just using the Nginx Hello World app for this demonstration because we want to keep it under the amount of time we need to be in. So what we have here is our template, and I'm going to, for time's sake, really quickly get the stage environment deploying. Make sure we get this up and running right away. So we're going to need to be able to see this so we can verify that our disaster recovery exercise actually works. And of course, we're doing the demo live because I like to take risks. And with the Cloudflare outages today, let's hope nothing else goes wrong for the demo. All right, there we go. Looks good so far. Okay, so while that's deploying, I'm going to walk through a typical module. So here I have my load balancer module that is being consumed in this template. This is a remotely managed module. This is in its own repository outside of the project. This is managed once by one team of engineers and then consumed on every project that we use. So in here, there's a few key components here. Number one is, of course, the README, ensuring that everybody who consumes this module has clear expectations of what it's going to do, what prerequisites they need to use it, what dependencies the module is going to have, and some examples of how to actually implement the module in code. The next thing we have here is our variables, which have defaults defined that will work in an actual environment, and validation conditions wherever appropriate. So we are actually including in all of our modules the requirement to actually validate the variables when they are input. Next thing we have here to ensure interoperability between different modules is we have a minimum versions file. So this declares what the minimum versions of the tools that we're going to use for each module are, so that when somebody pulls in modules from into a project, the different modules will actually talk to each other and say, hey, we're not compatible with each other's minimum versions. I can only go up to version 1.5. You require a minimum version 1.9. And it'll prevent somebody from trying to apply something, a configuration that doesn't actually work. The next really important thing we have here is our automated tests. So every module, as I mentioned in episode 2, has to be tested fully before it gets used in any templates or projects. So we have automated tests that run in GitHub Actions that run on every push to a monitored branch, every pull request, and every release. There are security scans that run on every single push. None of these will block people from doing ongoing development, but they will fail new release builds. So if somebody is trying to create a new release, if they don't have their tests passing, the release will not get created. Prevents risk downstream when a project team tries to actually implement. So examples of that, we have pre-release checks for validation. We validate that Terraform is formatted properly. We confirm that an init actually works. We'll run through our security scans. We will run through integration tests. All of this is done on every single release to ensure that everything we're doing is actually going to work in production. And then, of course, there's the change log. If you're having versions, you need to have a change log to keep track of what you're doing. What bugs are you fixing? What breaking changes are you making? And ensure that developers and other engineering team members downstream have a clear understanding of why they would need to increment their version. All right, let's take a look back at our deployment. All right, looks like stage ran perfectly fine. Before we get any more into that, I am going to bring up GitHub. Here we go. And just to show how this looks out here, very similar to what a developer's tools would look like if they were doing microservices and releasing versions. We have are releases available, and these releases can be pulled in to every single playbook. So anybody who has access to our private repositories has access to these released versions of these playbooks, these modules. And inside of our environment, that looks like this. So this load balancer in the dev environment is running version 3.0.0 of our load balancer module. These 11 lines of code are all it takes to provision a fully functioning load balancer. One of the powers of modularization here is that we can shift left all of the development, all of the coding practices, and when the downstream teams are consuming these, we can expose the configurations through easily understood parameters. So for example, in this case, because it's a development environment, I don't want to enforce the HTTPS requirements that we have for our production environments. So I have a flag that I can simply toggle that says HTTPS enabled equals false. And that will turn off the HTTPS listeners. It will prevent it from attempting to configure certificates, and it will essentially prevent all of the additional configuration that happens to make HTTPS happen at the load balancer. And to compare that to our stage environment, the only difference is instead of having that false flag, we're just going to tell it where to find the certificate that it needs to do to deploy HTTPS. And to show that that's working, we'll see. So if I go to stage-demo.software.com, and there we go. We're on HTTPS with a good certificate issued by AWS. We're in the US East 2 data center. Now, the power of this pattern comes from these modules and the configuration that's required to put them together. As I already mentioned, we're not writing any new code in the playbooks in the environments. There is no module code in this repository at all. Rather, I have these, I source them, I run init, my Terraform init. Terraform brings in all of the actual code necessary to build the modules. And in here, I can actually reference the READMEs and bring those out from the Terraform documentation that's been downloaded. And from here, I can get my samples and I can copy and paste those in to my environment and I can start using those. There's additional availability for overriding everything. We write modules in this pattern to be completely overridden. So everything that we have that is configured by default has a variable available to override it. And that is true of all modules. So our main.tf is a total of 90 lines of code, and that includes comments and whitespace for organization, and that deploys the entire environment. And this environment is a Fargate ECS environment sitting behind a load balancer with CloudWatch logs and a VPC with 4 subnets, 2 public, 2 private. So now let's talk about how this comes into disaster recovery. So one of the big issues that I had mentioned with disaster recovery is that it's easier to make changes in the console. With traditional IAC, that's actually true. It can be very difficult for somebody who is not a DevOps engineer to come into a Terraform playbook and say, okay, this is how I do that. Now in here, I can go and let's take a look at my modules. Let's look at Fargate, because let's say we need more resources for this container. Maybe this front-end container is pretty resource intensive and we need to double the memory. So let's look at our Fargate, look at our README. We can come in, we can find our examples, and we can see in one of our more advanced examples here, we have the information for how to declare CPU and memory. So as a developer with no actual infrastructure as code experience, I can come in here and understand how to take this code and move it into my actual environment and use it. How I can override the different parameters that are being used and how to deploy multiple of these with different sets of configurations. Okay. So of course, there's always a gotcha in everything you do, and disaster recovery is one of those things. So disaster recovery, and we're assuming in this case that our disaster is, I don't know, let's say AWS has a catastrophic DNS outage in their US East data centers. Not that that would ever happen. And now we can't access the data center to tear down the existing infrastructure. And so what we need to do is we need to rebuild the infrastructure in another location. However, our DNS entries are already being managed. And with declarative tools like Terraform, you can't just take that DNS and overwrite it. If it already exists, you're not able to go and manage it unless you import it. So for our disaster recovery scenario here, we have a script that we've written at Yahara Software, which will actually adopt resources into a disaster recovery environment. And so the script here is going to actually reach out, determine the DNS entry's resource identifier, import it into the disaster recovery state file, and then it's going to run our disaster recovery apply. So let's go ahead, move over to disaster recovery site and do start DR shell script. So there's going to be some output here as it goes through its discovery, attempts to find the DNS resource, and then import it into the Terraform state for disaster recovery. So when it finds it, it's going to do some manipulation because Terraform is case sensitive. And then it's going to do its import. Okay. All right. So while that's running, I'm going to point out the two changes between our stage and our DR playbooks. So the primary difference between the two is that in our variables, we're declaring a different region. That's the primary difference between the two playbooks. Everything being built off of remote modules that are already fully developed, tested, and able to run independently, we don't need to do any coding to tell this is going anywhere else. We simply change our region variable. The second thing here is because we don't want our disaster recovery site to be able to manage DNS unless we are in an actual disaster. So we want to be able to test disaster recovery without having to actually fail over the real production infrastructure. So our disaster recovery script here is going to build everything necessary. And then we have this flag here to tell it true or false whether or not it should be managing DNS. And that is reflected in our DNS entry here, where the CNAME records are only created if managed production DNS is set to true. So once we finish this first script, we'll have to go and set that, which I could have set that before we ran this script, but then I wouldn't be able to explain it as easily. So while we're waiting, set that, save it. And as soon as we are done, which should be just a couple minutes more here, we can run our apply again. It'll fail over the DNS to the existing new disaster recovery infrastructure, and we should be able to see that data center change reflected in the page that's being presented. Now, a couple of considerations with this. I've trimmed this scenario down significantly in the interest of time for this LinkedIn Live event. In a real disaster recovery environment, you would else be mounting your database snapshots at this time. And depending on the size of your database snapshots, that could increase the total time of your recovery. Generally, it's not that much though. Your recovery time with a couple terabytes of data could extend up to an hour if you have to mount databases and index them in a new, excuse me, mount snapshots and index them in a new database that's being stood up. So this strategy, again, works very well for disaster recovery because we are limiting the number of changes that can be made downstream. We are preventing drift by managing everything in our code in versioned modules upstream that are then consumed by developers and project teams downstream. Those consuming project teams cannot change the code underlying behind the modules. With that, we eliminate the potential for drift from code from one environment to the next. So we can have confidence that when we do our deployments, they are going to work. So let's make sure this is going to update our DNS. And so at this point, we have deployed an ECS cluster with a Fargate container service running on it. We have deployed a load balancer with routes and HTTPS enforced. We have brought in our certificate into the load balancer to properly enable HTTPS. And we've got our DNS. Ooh, the script didn't fail. All right, looks like we are good. So let's bring back up our demo here. And we are now in US West 2. We have successfully failed over our data center in code in a matter of minutes. And this was a cold site recovery. There was no infrastructure in place here when I started this recovery process. Now, to swing back, again, everything is fully codified upstream. There are no changes between the upstream and downstream modules, which means there are no changes between our various environments and how they've been codified. So I can go back once the disaster is over. Let's say AWS has recovered their US East data center's DNS. Now I can simply run our Terraform apply, and it's going to take back control of that DNS entry, reset it back to the US East data center, and we will be back to our original production infrastructure. All right, so we're going to change one DNS entry back to where it should be. Great, let's run that. And for the demo, I did set our DNS TTLs down to 1 minute so that they would refresh a little faster than we would normally have in a production environment. So hopefully we should be able to see this change reflected relatively quickly here. And there it is. We're back to the original environment. All right, so to recap, The reason that codified disaster recovery typically fails in a cold site scenario is because we have unmanageable drift between environments. That unmanageable drift is caused by the codified solution being too complex to use and leading to developers and downstream project teams choosing to do their changes, break fixes, and other types of changes in the console in their cloud environment. This increases the cost of maintenance because now we're adding technical debt. That technical debt is making our disaster recovery scenario require warm or hot site to be reliable. If we can close the knowledge gaps, eliminate that technical debt, follow good coding patterns in our IAC, we can eliminate that drift and enable cold site recovery across the board. We don't have to have a hot site available 24/7 to have sub-hour recovery windows. We just have to do our code right. All right, so next week we are going to, second, let me get the slide here up. Current slide. So next week we'll be talking about waste management, and we are going to go through two general topics here. Number one is what is available in cloud native tools. So we're going to talk about the actual cloud native tools that everybody has available to them. We'll use AWS as an example again, because it's kind of been the theme here. So we'll look at AWS Cost Manager, and we will go through how to understand what you're spending money on and what's actually in use, and your 100% inventory of everything you own in the cloud across all regions. And then we're also going to look at a codified tool that will help you estimate the cost of everything you deploy. So we're going to implement in a pipeline the ability to review cost and create alerts that will tell our FinOps team if a production deployment or, well, any environment deployment is going to increase the cost of maintaining that environment over a given threshold. All right, as always, thank you for joining me, and I look forward to seeing you next week.